today's talk is by E.Hałubek, and the title of this talk is Derivation and Implementation of a Linear and Roton Qubit Inspired by a Non-Uniform Transmission Line. Eric, go ahead.
Thank you for the introduction. So let's begin. Presentation content. Firstly, I will say something about the motivation behind the research. Then we'll discuss research objectives. Then I will show a quick theoretical introduction, experimental setup, then results of the experiments, conclusions, and future research plans. So what's the motivation behind it? The motivation. So let's begin with showing what explaining what analog computing is. So analog computers are computers that operate on continuous signals, which is in opposite to the digital electronics that use discrete signals. And here is an example of such analog circuit that could be used to integrate electrical signal. It consists of capacitor, resistor, and operational amplifier. So it is possible for some cases to use analog devices to compute some things. However, there are also some applicability issues corresponding to this approach, because analog systems are currently quite difficult to integrate with digital systems, tend to cause interference and have many parameters that we wouldn't like them to have, like parasitic resistance and inductance. However, because in certain situations it is better to use analog over digital approach, there has to be something about it that's useful and unique. So we all know that even quantum computers have difficulty simulating complex systems with any interacting bodies. And what we are aiming for is something that maybe in the future will be able to act as an analog computer that would be able to simulate the interactions between very complex quantum scale objects. So, analog signal can be used to do that because it's a direct representation of reality. It's continuous, and it doesn't have to be processed to digital discretized version, which saves a lot of energy. So the main research objective is to create a Schrödinger equation solver based on analog circuits. We all know that this equation can be solved analytically for hydrogen atom, but for other complex systems, it's much more difficult, and we don't know how to do it analytically. So we use very complicated and technically expensive computational methods. But if we used an analog circuit to for such purpose, we could obtain instant results with very little energy consumption because we wouldn't there would be no need to convert the signal and the information that is within the signal to digital version, which could be processed by a normal computer. So that's where this energy save comes from. Okay, so this work is based mostly on Krone's model. Gabriel Krone was an engineer that lived in 19, 19, 1930s, 1940s. And he was known of this model that shown that the Schrödinger equation could be emulated by an electrical circuit. And here's an example of the circuit. It's only a part of a very long line of capacitors and inductors. Mm, and this particular piece of the circuit is the most important because it represents the place where we have potential well. In this case, it's rectangular potential well. So its rectangular potential well is realized by putting out the inductors from the middle of the circuit. In this case, we have three capacitors without the inductors L1 being connected to them in parallel. But in a general case, it would be possible to make it even more. And it would be better if we had, the more we had these capacitances without inductances, the better and more accurate the results would be. So now let's talk something about theory behind it. So the Schrödinger equation could be expressed as we see here, where delta x is a discrete step in space, which we can see here being, okay, so maybe it's a bit difficult to see, but it's a distance between the nodes. That's what delta x is. The distance between each node, it's a constant distance between each node. So that's delta x. And that's how we could represent the Schrödinger equation. Okay. So in this model, wave function is represented by a value of voltage of the amplitude voltage of, we could measure peak to peak voltage in our circuit models that we could observe on an oscilloscope screen. That's the most basic interpretation. So if we wanted to measure this voltage, here is in the bottom line is the ground potential 0, and we measure the voltage of a sine wave because we are applying sine wave to this circuit. The voltage of a sine wave peak to peak value from the ground potential to these nodes. So at each node, the sine wave will have a different amplitude on oscilloscope screen if we wanted to measure it. And here, where we have the potential well, the value of this voltage would be the highest. Okay. So transforming the equation, the second equation here, we could write delta h of x, which is Hamilton operator, times psi of x, as delta x times minus h h bar squared divided by 2m times d squared by dx plus v of x, which is a potential, times psi of x. Then using a numerical representation of a derivative, again, delta x is a discrete step in space, the smallest step that we could make. We could use such definitions of derivatives to rewrite this expression when we have second derivative operator and as something like that, which could be simplified to the following expression below. Okay, so now using this expression, we could write the for the second equation in the form of equation shown here. There are just basic transformations. Okay, so also how it works, it's shown in the figure 3. This is a representative fragment of Cron's circuit model, which shows how different currents flow in each section of this piece of the circuit. So there is current I of x that is divided to the current I of x plus dx and current delta I of x, which is flowing through the branch. And it happens in each branch, but we have only two because for simplicity. So this current flows here to the ground potential in each branch like that. So this delta I of x current is expressed as follows. And now using that we have some other excuse me, we have some other equations. So then the value of delta x, the delta I of x current could be determined by Ohm's law. So here we can see that there is a capacitor and an inductor. We could calculate the total impedance of this branch as an impedance of the capacitor with inductor, which then we could using that we could write the following equations. So here we have actually admittance, which is the reverse of impedance. It's 1 divided by impedance, and impedance, the reverse of impedance could be right as follows. Okay, and then when we have it, then we could write the equation 6, which shows the delta I of X current flowing into the branch, as is shown in equation 8. So this current will depend on the place on the branch of a circuit. It will be different in each branch. So different here and different different from the current that's on the left and that's to the right. Okay. Also, I like to think about it as about this delta I of X current as the potential energy flowing out of the node, each node of the branch, and transforming into kinetic energy. So we could imagine that this potential energy flows out of each branch, and so it flows out, and then we have a potential well in the middle where there is where the potential energy is the lowest. Mm, it's because when we have no inductor, the current delta I of X flowing through the through its branch is higher. In the case of circuits that we created, it doesn't have to be like that because it depends on the value of this inductance. But in using the values of inductances that we applied, it would be like that. Okay, so this expression, equation 8 for delta I of X current could be then transformed to expression equation 9, as we can see here, where the potential V corresponds to the wave function. Okay, and here we can see in the figure 4 how different operators could be represented in our circuits, in our circuit models. It's obviously it's for a particle moving direction in one dimension. Good. So if we took a more precise approach to the derivation, we could use the knowledge that we acquired in previous part to derive the Crohn's model, the actual Crohn's model. So the v of x is minus dx j l omega I of x, where v of x is a voltage phasor and I of x is a current phasor, and the I of x equals dx times 1 over I 1 over j L1 omega plus j omega C1 times v of x. And after simple rearrangement, we get the derivatives as shown in equation 11. And that results in equation 12, assuming that L is constant. Okay. So the last equation, equation 12, could be rewritten in the form of equation 13. And this equation has the analytic solution as shown here. Okay, so for the case of circuit elements, connected in parallel, we obtain the following equations. Now these equations could be decoupled if all capacitive, inductive, and if all capacitive, inductive, resistive linear density elements are position independent. In the next step, non-linear elements are incorporated to the models shown in figure 2. So these models. So let's consider a linear circuit with linear density L of x, L1 of x, and C1 of x. Then we could write the following equation 19, which implies the equations shown here. And the last equation implies the second order equation with the derivative term d by dx times 1 over j L of x omega. As we obtain the harmonic oscillator equation. Now, under the assumption that L of x is constant, this equation transforms to equation 23, which is similar to the Schrödinger equation of the following form. So here we can see how each part corresponds. For example, effective potential corresponds to the value of 1 over L1 of x. That's probably the most important. And we can see that the total energy is related to omega squared times C1 of x. And L, 1 over L of x plays the role of h squared divided by 2m. Now, we'll discuss the experimental setup of a circuit that we prepared. And so here we can see a circuit diagram that was created using anti-spice environment. It has 19 nodes, so places where these branches connect to the upper line, and the values of capacitances were 1 microfarad, and all inductances had values of 1.5 millihenry. The sine wave signal was applied to the middle of the circuit because the circuit is symmetric. Okay, so here we can see simulation results for this type of circuit on the horizontal axis. We can see the node number and then the value of voltage, of the peak-to-peak simulated voltage of the sine wave for different frequencies. So we have frequencies 800 hertz, 1500 hertz, 2000 and 2500 hertz here. And we can see that for 2000 hertz, this curve is the most similar to the cosine function, because this simulation was conducted for the square wave. Okay, and here is a different simulation, and also on the same circuit, just for different, for higher frequencies. And we can see that higher frequencies like 3000, 4000, and 5000 hertz correspond to different states, which was not so obvious in case of lower frequencies. These curves looked almost the same. Okay, and here are the actual measurement results from our experiments where we measured the voltage, the peak-to-peak voltage on each node using oscilloscope. And as we can see, for each node, we have here a value in millivolts of this peak-to-peak voltage. The different frequencies mm, represent different states as well. Ground state is represented by blue points, and the frequency overshooting is green points. Okay, now there's also an interesting example of in some way similar circuit called the roton circuit that represents a particle trapped in a circular shaped tunnel. And so that's how it looks. Obviously, it could be transformed into a more linearly, um, linearly placed, linearly, yeah, linearly placed circuit, as we can see here. So this Roton circuit was also constructed by us, and we measured the voltage values, again peak-to-peak values in each node. So we can see that actually this Roton circuit is something like one linear qubit connected with the other that is symmetrically um, like it's mirrored, like the mirror symmetry um, in relation to the upper part. And the difference is that we also added here an inductance of 1.5 millihenry. So here are the experimental results from our measurements. We have 26 nodes, and the numeration of the nodes is that we started from the first node is here, the second here, third, and for the 14th node is here, and there's a transition. So here's node number 14, 15, 16, 17. And we can see that this transition taking place here. So as we can see also for different frequencies, we have different states. We made some simplifications in our circuit analysis because the inductors and capacitors and resistors, all electrical components, are not perfect. They have some properties that we wouldn't like them to have, like equivalent series resistance in case of capacitors, and also in inductive properties, but this corresponds more to resistive elements, to the resistors or other elements. We actually didn't use resistors. However, we should also consider probably in future simulations the resistance of inductors, because our models do not um, consider this resistance value in each inductor, which is in the case of our components like 4 ohms per each inductor. We don't actually know what's the equivalent series resistance for our capacitors, but well, maybe that's a part for future research to do to investigate that further. And so what are the conclusions? The conclusion is that it is possible to generalize the circuits proposed by Kron to represent a confined particle by different shapes of effective potential, and the quantum roton model that was implemented by us confirms the theoretical framework. In the future, we will be focused on the two alternative, especially on these two alternative types of circuits. So these are only representative pieces of the circuits that using which we could construct the whole circuit by adding them together to each other. And we will be focusing on the miniaturization of our circuits, and maybe in the future also development of small classical chips simulating quantum phenomena locally. And that's it. That's the end of my presentation. Thank you.